तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello everybody. In the series of lectures on basic electronics, learning by doing, we now come to the fourth of the series. Before we go on to the lecture, we will look at what we saw in the previous lecture. In the previous lecture, we studied about resistors in combination. For example, series and parallel combination of resistors, potential dividers, how voltages can be divided and a smaller voltage can be obtained from a larger power supply by using a set of resistors in the potential divider form, and then something about capacitors, different types of capacitors, electrolytic capacitors, non-electrolytic capacitors and things like that. And we also briefly saw something about coils and transformers, the inductances and transformers, which are very essential in several electronic circuits. In this lecture, we will look at some of the useful laws and theorems. We have already seen one very important law, which is basically Ohm's law. We have seen that. We also did an experiment to see how Ohm's law is obeyed. When I have a voltage source and a resistor, the voltage across the resistor is proportional to the resistor and the current is proportional to the voltage when the resistance is constant. All those things we have seen already. Now, before we go further into the laws and theorem, I thought we will just briefly look at what is a constant current source. We should first know about current sources. We have already seen about voltage sources in the previous lectures. Now we will study about current source. Just as voltage source is something which gives a voltage output, obviously you can understand current source is something which gives a current output. The constant current source is something in which the current is a constant, just as you have a constant voltage source where the voltage is a constant irrespective of the value of resistance I connect across the output terminals, the voltage will remain constant. In the same way, in a constant current source, irrespective of the value of the resistance I connect in the circuit, the current will always be a constant. The constant current source is basically different from the constant voltage source. If I have a simple circuit with a voltage battery or a voltage source and a resistance and all that, you already know that every voltage source is also associated with an internal resistance. Therefore, when I look at a voltage source, I should always remember there are two things in this. One is an ideal voltage source which has got zero internal resistance. Added to that is an internal resistance which is corresponding to the voltage source that we are looking at. Therefore, any given voltage source can be equivalently represented by two items. One is an ideal voltage source which has got zero internal resistance, as you all know, and a series resistance which is actually the internal resistance of the voltage source that we have. In the similar manner, if I have such an arrangement, for example, if I connect any load or any resistance, load means resistance, then you can imagine the moment I connect a load, the value of the current in the circuit will be different, because current by Ohm's law is given by voltage divided by total resistance. The total resistance in this case is the internal resistance of the voltage source plus RL, the load resistance that I have connected. So, you can imagine immediately that the current in a circuit of this type will always depend upon the resistance that I connect as RL. Now, when will this current be a constant? When will this current remain constant in spite of the resistance that I connect as RL? You can immediately see that only when I have very large resistance as the internal resistance of the voltage source, you would find the external resistance that I connect cannot alter, because it has been decided already by a very large value of internal resistance, and therefore the external resistance, which is much smaller than the internal resistance, cannot alter considerably the current in the circuit. So, you can immediately recognize that a constant current source should naturally be characterized by a very large internal resistance or internal. So, how do I define a constant current source? A constant current source therefore can be looked at as something which has got a very large voltage source, very large value of voltage source, in series with a very large value of resistance. Together they can form a current source. The current value is decided by these two. For example, voltage divided by the internal resistance will be the current that you will get. Because the internal resistance is very large value, whatever value of resistance that I connect which are smaller considerably with reference to the internal resistance, you would find they will have no control on the current, and therefore the current output will remain a constant for several ranges of resistances I connect at the output. So, if I now extend this concept and then look at an ideal current source, the moment I say an ideal current source, you can immediately imagine that an ideal current source should have infinite internal resistance. Because I say ideal, I can go to the maximum value that I can think of. The maximum value is infinite resistance. So, an ideal current source is characterized by infinite internal resistance. Obviously, because it is ideal, it cannot be practiced, it cannot be realized in practice. Similarly, in an ideal voltage source, you may perhaps recall the internal resistance will be 0. In a no practical voltage source, the internal resistance can be 0, and therefore they are all not ideal. Then we can, the other point I wanted to stress is that we can build a constant current source by employing a very large voltage source and a very large resistance as an internal resistance. These two combination along with an external resistance will form reasonably a good constant current source. So, let us go with this background, and I also show you on the screen that an ideal current source will have infinite internal resistance, and we have to compare this with an ideal voltage source which will have 0 internal resistance. The circuit symbol of a current source is shown here, which is just a circle with an arrow inside. The arrow direction shows whether it is a source or a sink. The IS here is I means current, S means source. So, IS is a current source, and the arrow indicates that it is a current source. It can also be a current sink. When I invert the arrow that you see on the screen, then the current will be in the other direction. It will be flowing towards the ground. Therefore, current will have to come from the outside load into the ground, and therefore this becomes a current sink. So, except for the direction, the property of the current source and the current sink are identical. You do not have any confusion about it. So, this is, you would find such important concepts will be coming again and again in various circuits, and therefore you should remember a normal voltage source will always have an ideal source, voltage source with a series resistance, and an ideal a normal current source is also will have an ideal current source and an internal resistance which is of very high value. These two concepts we should remember for all our future applications. Now, there are also other concepts which perhaps you already know. I assume all of you have got a background in basic electricity, and therefore you would have seen Kirchhoffs laws, Kirchhoffs voltage law and Kirchhoffs current law. But for completeness, let me briefly review the concepts of KCL or the Kirchhoffs current law and KVL, the Kirchhoffs voltage law, quickly. Now, what is Kirchhoffs current law? At any instant, you can see on the screen, at any instant the sum of all the currents flowing into any circuit node is equal to the sum of the currents flowing out of that node. What is a node? A node is a point where you have several wires or several current conducting wires come together. Therefore, it is a junction point of several wires. So, if I have such a thing, then what Kirchhoff says is that whatever current that is flowing in towards that point will have to flow out. There can't be any storage or staying of current in such nodes. This is the essence of KCL or current law. Now, I have shown it on the screen with an equation. Sigma, that is the sum of I in, all the currents flowing in to the node, is equal to sigma of I out, the sum of all the currents going out. This can also be explained in a slightly different way. In other words, at any instant, the algebraic sum of all the currents at any node, circuit node, is 0. That means, if I add all the currents algebraically, what I mean by algebraic, if the current is flowing into the node, it is positive if I assume, then if it goes away from the node, it is negative, and therefore, the total current, algebraic sum of all the current across this at this node will be equal to 0. Therefore, the equation sigma of I equal to 0 represents this concept. You can use any of these. You can either say current flowing in is equal to current flowing out, or you can say the algebraic sum of all the currents flowing into a node is equal to 0, where automatically you take the vector direction of the current, whether the current is flowing in or flowing out. Now, I have just shown in the next screen a small example where you can see I have shown a node which is this central point. You can see currents are coming from different directions and they are also flowing out from the node in different directions. Now, I1 is, for example, 1 ampere which is flowing into the node, I2 is 2 amperes flowing out of the node, and I3 is 2 amperes flowing into the node, I4 is again flowing into the node 4 amperes, I5 is minus 1 ampere flowing out, I6 is 4 ampere flowing out. Now, if I want to apply Kirchhoffs law, then I should sum all the currents flowing into the node. That means, you can see here current flowing into the node I in is equal to I1, I1 is flowing in which is 1 ampere, I3 which is also flowing in which is 2 amperes, and I4 which is again flowing in which is 4 amperes, and if I add them 1 ampere plus 2 ampere plus 4 ampere, that gives 7 amperes. So, the current, all the sum of the current flowing into the node is 7 amperes. Now, if I look at the current flowing out of the node, I out in the next line, you can see it is I2 which is actually 2 amperes, I5 which is actually 1 ampere, and I6 which is 4 amperes, and we combine them all together, again you find it is equal to 7 amperes. Therefore, I in, the current flowing in to a node, is equal to I out, the current flowing out of the node. In this case, both are 7 amperes. The other way to do is to look at the algebraic sum of all the currents. That is what I have done on the right side. The algebraic sum is I is equal to I1 plus I2, I3, I4, everything I sum it together, and then but make sure that if it is flowing in, I keep it as positive. For example, I1 is taken as 1 ampere plus, and I2 is minus 2 amperes because it is flowing out, and I3 is plus 2 amperes, I4 is plus 4 amperes, it is flowing in again, I5 is minus 1 ampere because it is flowing out of the node, I6 is minus 4 ampere, again it is flowing out of the node. And therefore, if I now find the total, you can find the total is 0. Therefore, the algebraic sum of all the currents flowing into a node is equal to 0. In both ways, you find that Kirchhoff's current law is obeyed. Now, I have given an example. What is the advantage of knowing the Kirchhoff's law? You can see in this figure, I have got one node in which one current which I don't know. I want to find out what is this current. I have all the other currents. I know all the other currents. So, if I look at the simple way of looking at it is algebraic sum of the current flowing into the node should be equal to 0. So, I, which is this current which I don't know, plus I1 plus I2 plus etc., all the things I put together should be equal to 0. Now, I don't know, plus I1 is 1 ampere as you can see in the figure, and I2 is 4 amperes. So, plus I3 is again flowing into the node 2 amperes, I4 is flowing out of the node, therefore minus 4 ampere, and the next I5 is plus 3 ampere, I6 is plus 4 ampere, I7 is minus 3 amperes because it is flowing out, and if I look at the total and evaluate, I can always get the value of I, which I do not know. Now I is equal to minus 7 amperes. So you do not have to worry about the direction of the current in this case, because automatically the sign will show what is the direction of the current. Because we have taken all currents flowing into the node as positive, I get minus 7. Therefore in this I, the direction of arrow I have shown here, which I did not know at that time, is actually the wrong. It should be in the other direction, because now after solving the problem with Kirchhoffs law, I find the current is flowing out and the magnitude of the current is 7 amperes. Now let us move on to the next, which is Kirchhoffs voltage law. Just as we have Kirchhoffs current law, the Kirchhoffs voltage law is also very useful in solving simple network problems and then trying to know unknown voltages. And Kirchhoffs at any instant, Kirchhoffs voltage law says at any instant the sum of all the voltage sources in any closed circuit is equal to sum of all the voltage drops across different resistors and inductances in that circuit. So you can see this is another law of Kirchhoffs, which again talks about, in this case, a closed circuit. A closed circuit can have several voltage sources or batteries and several resistors connected, all connected in series or parallel in different combinations. Now another way of saying that, what is that? It says if I sum all the voltage sources together, that should be equal to all the voltage drops across different resistors that I have used. The other way to do that is, I can always look at in the same way as in the KCL, the algebraic sum of all the voltages around a closed circuit across different components should be equal to 0. In this case, in equation you can see sigma of E, where E represents the voltage sources, all the voltage E1, E2, E3, several of them, minus sigma of IZ, which is I into, actually I should have put an R here. So the voltage drop across different currents, this I into R will give me the current, the voltage drop across different resistors. They must sum up together to 0. That is what KVL shows. Now let me just take an example. You see on the screen there is voltage source V with the polarity shown, and 3 resistors R1, R2 and R3 all connected in series to this voltage source. Now what Kirchhoffs law says is that this voltage V should be equal to, if there is a current I flowing through that, which we know will be I into R1 plus I into R2 plus I into R3. So the voltage drops across the 3 resistors are I into R1 across R1, I into R2 across R2, I into R3 across R3. If I add them all together, because you find they have the same sense of direction. For example, current entering is plus, current leaving is minus, again this is plus and minus, therefore you can see all of them can be added together. But if you come here at the voltage source, you find I am coming from minus to plus with reference to voltage. Therefore if I want to add them algebraically, if I take V as positive, all the other things will have to be minus. So in the second line you see V minus I1 R1 minus I2 R2 minus I3 R3 is equal to 0 is one form of KVL, or V, the total voltage source in the circuit loop, is equal to I1 R1 plus I2 R2 plus I3 R3, which is written here. So either you can equate the total sum of the voltage sources to the voltage drops across different resistors in the circuit, or you can say the algebraic sum is equal to 0 across a closed loop. So this is Kirchhoffs law. We will quickly go on see the Kirchhoffs law on the table, and then we will come back and look at another example of Kirchhoffs law where it can be employed. Here I have the breadboard, which you are now familiar with. Okay, you can see I have 1, 2, 3 resistors connected in series, and this red wire is going to the power supply here, which is showing 6 volts. So, I am connecting 6 volts here, the ground is common, this point and this point are ground, this is connected to plus of the power supply. There are 270 ohms here, 220 ohms and 100 ohms all connected in series. So, it is a very simple circuit. You have one voltage source and 3 resistors, that is what I have shown here. Now, if what Kirchhoffs law says is that this voltage 6 volts should be dropped across all these 3 resistors totally. Therefore, if I know the current I into R1 plus I into R2 plus I into R3 should be equal to 6 volts, that is what it says. Now, what we will do, we have a multimeter which I have switched on and I have connected to voltage, and it is now measuring DC volts. So, I have the 2 leads of the multimeter. Now, what I would do is I will measure the voltage across each of these. For example, let me connect this to ground, one of the terminal, the other terminal I connect here to the positive end. Now, you can read, it is reading 6.04 voltage, I suppose you can see that. So, what I have applied is 6 volts. I have measured that, this is a voltage source. Now, what I am going to do, I am going to measure the voltage across each of the resistors. So, let me connect to one end of the resistor the negative terminal of the multimeter, to the other end I connected the positive terminal. So, now I have connected the voltmeter across the 270 ohms here, and the voltage is around 2.77. I hope you can see that the voltage here is 2.77 voltage. Now, I will remove the voltmeter from across 270, I will connect across 220. So, I connect the positive to one end, I connect the negative to the other end. Now, let us read what is the voltage. That was the previous one was 2.77, now it is 2.24. So, if you add them together, they come to approximately about 5 volts, and now the last resistor is R3 100 ohms. I will connect the voltage voltmeter across this 100 ohms here and at the bottom, and you can see the voltage is about 1 volt. So, totally 2.77 plus 2.24 plus about 1 point something together gives me 6 volts approximately. So, you can see whatever voltage I connected here is divided across each of these resistors. As Kirchhoffs law says, the voltage source should be equal to I1 R1 plus I2 R2 plus I3 R3, and therefore, Kirchhoffs law is verified. Now, let us take a different example, another example. Okay, let us take a second example. In this case, you can see it is a slightly more complicated circuit. It has got 3 voltage sources, V1, V2 and V3, as you can see on the screen, and it has got 3 resistors R1, R2, R3. So, they are connected in this way, and now you can see you have 2 loops. There is one loop in this direction, as you can see on the screen, and there is another loop here which involves V2, R2, R3 and V3, right. So, if I now try to apply Kirchhoffs law for this, then you can see V1 minus I1 R1 minus I1 minus I2 R2, because I assume the current here is I1, here it is I2, here it is I3. So, I2 minus I1 is the current flowing through R2 minus the V2, that should be equal to 0. The algebraic sum of all the voltages V1 current, the voltage across R1, the voltage across R2 and the voltage V2 all together should equal to 0, and similarly for the next loop V2 minus I2 minus I1 into R2 then I2 into R3, that and V3 the voltage source, this together the sum, algebraic sum should again be equal to 0. So, by using this you can find out the unknown value of resistor or unknown value of voltage across any of the resistors and things like that. So, these Kirchhoffs laws are very useful in solving several problems. Now, let us move on to another very important theorem in electronics, which is maximum power transfer theorem. What do we mean by that? If I take the small example, I have a battery here which is connected to two resistors, Rs and RL. What is this Rs? This Rs and Vs, as you can see, is nothing but an actual voltage source. Any voltage source can be represented by an ideal voltage source Vs, which has got no internal resistance, and Rs as the series internal resistance across that. So together they form any actual voltage source. RL is the resistance I want to connect this voltage source to. Now I have two resistors in the circuit, Rs which is internal to the source and RL which is connected externally by me. Now what is when will the maximum power be delivered to RL? There are two resistors, therefore the voltages will be shared. You know that series resistors share voltages. So these two resistors will share the voltage, and the power is nothing but voltage into current. So Rs into I, RL into I will give me the voltage, or I square RL and I square Rs will give me the power across these two. Now if I short this, that means when I have zero resistance, this is shown in the last figure here, when the RL is 0, that means I short this to remove this RL, connect it by a short, that means it has got 0 resistance. So the power is I square R is 0, and therefore the power becomes 0, and the voltage also is 0, as you can see, and therefore you can have a 0 power when I have short, and when I open, that means what? I just release the RL or the 2 and keep the two terminals open without connecting anything. If I have that, you can see, because I have an open circuit, this corresponds to infinite resistance. RL now is infinity, and I is also 0, because if I have infinite resistance, the current will be 0. So here you have a case of current being 0, and therefore what is the power? I square R. I is 0, and therefore power is 0. So in both these cases, when I have a short or when I have a open, the power delivered is 0. So these are the two extreme cases. Somewhere in between, if I keep increasing the value of resistance RL from 0 to some value or up to infinity, how will the power be changing? That is what we are looking at. When will the power be maximum with reference to the voltage source? When can the voltage source deliver maximum power to the load resistor? It cannot be at 0 value, or it cannot be at infinite value, that we have already seen. So when can that provide maximum load? The theorem says that the maximum power will be delivered only when Rs is equal to RL. Rs is the internal source resistance, RL is a load resistance. So when the value of the source resistance and the load resistance match, they are equal, then there is maximum power transfer. You should always remember, this is different from the condition, when will I have, for example, when will I have maximum voltage across RL? You can see maximum voltage, the voltage is divided by the two resistors, because series resistors divide voltages, and the voltage division will be proportional to the resistance, and therefore the larger the value of resistance, the larger will be the voltage across RL, and therefore when I want maximum voltage, you find RL should be maximum with reference to Rs. But when I want maximum power, not voltage, then you find RL should be equal to Rs. That is what maximum power transfer theorem says. Now we can list out all the various relationship between the load resistance, voltage value across the load, current across the load, power across the load by the set of equations that I have shown on the right here. The condition for maximum power transfer is RL should be equal to Rs, the internal resistance. VL, the voltage, will be Vs by 2. Why? Because Vs is the total voltage, RL and Rs are equal, and therefore the total voltage should be divided equally among the two resistors. Therefore the voltage across the load will be half of the voltage source. Similarly, the current across the load IL will be VL by RL, we all know that, and if you substitute this value of VL, Vs by 2R, and the power is multiply voltage by current, you will find VL square by RL, that is the power V square by R, or it is Vs square by 4R. So this is a maximum power. Vs square by 4Rs is a maximum power that will be delivered to the load RL. Okay. Now how do I get this? How do I say RL is equal to Rs? Is there a way to prove? I have just briefly taken a simple way of proving it. PL, the power output, is voltage into current, that is power, definition of power. What is voltage in this case? Vs into RL by Rs plus RL, because we have already seen RL and Rs provide a potential divider. The voltage across RL is total voltage multiplied by RL divided by RL plus Rs. This we have already seen, that is the voltage. Similarly, the current is voltage divided by total resistance. Vs is the voltage, total resistance is Rs plus RL. So this is a total power. So Vs square, when I simplify this, it is Vs square RL divided by Rs plus RL whole square. So this is the value of PL. When I want maximum PL with reference to RL, I can differentiate. All of you know calculus, dou PL by dou RL should be equal to 0 if I want maximum value for this, and dou square PL by dou R square should be negative if I want maximum. If this dou PL by dou RL gives me 0, gives me a extremum value, either maximum or minimum, and dou square PL by dou R square tells me whether it is a maximum or minimum. So we can find dou PL by dou RL for this function from our knowledge of calculus, and I have done that here. Vs square Rs plus RL whole square minus RL into 2 into Rs plus RL divided by Rs plus RL whole square by the V by U formula, and you can see that means ultimately when I simplify, Rs plus RL minus 2RL divided by Rs plus RL whole cube should be equal to 0, from which I can say Rs minus RL should be equal to 0, or in other words Rs should be equal to RL. That is what the maximum power transfer theorem already mentioned. Thus, when the load resistance RL is connected to a voltage source Vs with a series resistance Rs, the source has got series resistance Rs, then maximum power transfer to the load occurs when RL is equal to Rs. This is a very, very important concept in electronics. Later on you would find when I build an amplifier and connect it to a loudspeaker, usually loudspeakers are coils with magnets and a diaphragm and all that, you all know that. So when that means it is a simple copper coil, and the resistance of the copper coil will be very, very small. An amplifier is something which will magnify an input voltage at the output to a large value, and during that process you would find when I look from the outside of the amplifier, you would find the amplifier can be imagined to be a voltage source with a resistance, the internal resistance that we already talked about, and that resistance can in general be a very large value. And therefore, when I connect an amplifier directly to a loudspeaker, you would find there will not be any power transfer at all. That means the sound output from the loudspeaker will be very minimal unless I make the internal resistance or the output resistance of an amplifier is equal to the very low resistance of the loudspeaker. I will not get any sound at all. So one has to be very careful while connecting a loudspeaker which is a very low load, very low resistance load, to an amplifier which might have a larger output resistance, and there the concept of maximum power transfer comes directly, and therefore it is a very important theorem. Now maximum power transfer can also be looked at in terms of current sources. I took only the voltage sources, but you can also look at in terms of current sources. I have shown a circuit here. I have a current source, and the current source has got an internal resistance which is called Gs, which is represented here in conductance. Gs is source conductance. Source conductance is 1 by source resistance. You know that conductance is 1 by resistance. So it is nothing but 1 by RL, 1 by Rs, and the load resistance is also represented by a load conductance GL, which is nothing but 1 by RL. And therefore, for maximum power transfer, RL should be equal to Rs, we have already seen, which in this case corresponds to GL is equal to Gs. 1 by RL should also be equal to 1 by Gs, 1 by RL, or GL is equal to Gs. Similarly, IL is equal to IS by 2. Here the current is dividing because GL and GS are in parallel. You know that parallel resistors divide current, series resistors divide voltage. parallel resistors divide current here, and because they are equal, the two resistors, current divides equally, and therefore IL becomes Is by 2, the source current divided by 2, and the power PL is IL square by GL, or in terms of GS, Is square by 4 GS. So this is the law corresponding to constant current sources when you employ and look at the maximum power transfer theorem. There is also another case where instead of DC you can think in terms of AC circuits. When you have AC circuits, you will not only have simple resistors, you will also have reactances or impedances, like for example capacitive reactance or inductive reactance. So in general you can call them as load impedance, ZL. So when a load impedance ZL is connected to an alternating voltage source, AC source Vs, with a series impedance Zs, in that case we also call the internal resistance as internal impedance, right. So that is Zs. So maximum power transfer to the load occurs when ZL is equal to Zs star. What is a star? The star is the complex conjugate of ZL. Normally you will represent ZL as R plus J times XL or XC or whatever, depending upon whether inductive load or a capacitive load. Therefore generally it can be complex, that means the phase can be different even though the magnitude can be the same. So you would find ZL and Zs should obey the relationship that ZL should be equal to the complex conjugate of the Zs, which is the internal impedance. So this is what the maximum power transfer says with reference to impedances in alternating current sources, which actually if you look at it as RL plus XL or XS, then RL are the real parts, RL and RS of the two complex quantities ZL and Zs, and RL should be equal to RS, and XL and XS, XS, which XL is the reactance of the load, XS is the reactance of the source. These two should be equal but opposite in direction, because the complex conjugate they will be opposite in sign, and that is what the maximum power transfer says with reference to impedances. Now let us move on to another theorem which is again very important in solving network problems, and that is superposition theorem. Superposition is a very important concept in electronics as well as in several other fields of physics. For example, superposition of waves you have heard. What do you mean by superposition of waves? If in a medium there are several waves, the resultant amplitude due to all the waves present at any given point in space is nothing but the sum of the individual amplitudes of each of the wave. We have also seen similar situations with reference to mixture of gases, for example. Dalton's theory of partial pressures that tells you that if I want to measure the total pressure due to a mixture of gases, then all that I have to do is I should assume I should fill the volume with each of the gas independently and find out what is the pressure at that point due to each of the gas independently, and ultimately I will add all these values together to obtain the total pressure due to the presence of all the gases simultaneously in the volume. So superposition theorem is very useful in several fields, even in quantum mechanics, in physics. For example, superposition is a very important concept. So let us look at the superposition theorem with reference to electricity and electronics, and the superposition shows it helps. In what way it helps? It helps in determining the various components of voltages and currents in different segments of a circuit, in branches of the circuit. So it is very important and very useful. Now how do I do that? In any given circuit you can have more than voltage source, one voltage source. You can have 2 or 3 voltage sources, you can have several resistors. Now let us confine ourselves to simple cases of resistors and voltage sources. Then if you look at that, how do I find out a current through any one resistor due to the presence of several voltage sources? Then the superposition theorem tells you, just as in the other case, assume that all the other voltage sources are not connected in the circuit, assume only the one of the voltage source is connected. Now calculate what is the current through the resistor due to only one of the voltage source. Then remove that voltage source, introduce the second voltage source. Find out what is the current through the same load due to the second voltage source. then remove the second voltage source, introduce the third voltage source, find out what is the current. So finally you cover all the voltage sources in the circuit one by one like this and obtain the current due to each one of these voltage sources and sum them all together at the end. Algebraically you sum. Some may provide current in one direction, some may provide current in the other direction depending upon the magnitude of the voltage and the sign of the voltage source, how it is connected in the circuit. So in general this total current, if I add, that is the current I will get when all the voltage sources are present simultaneously in the circuit. This is what superposition theorem says. It is a very simple, but we can understand obviously, but then if you really look at it in solving problems, it is very useful. Once it is put as a theorem, it becomes very convenient for us to apply the theorem and solve very complicated situations in electrical and electronic circuits. So I have listed many of the important points that we should remember in the superposition theorem. There are two or more energy sources you can have. The sources are either voltage or current, you can also have current sources. The circuit is not too complex. If it is too complex it becomes very difficult. Maybe in a simple case we can easily do that. There are 5 steps used in applying superposition theorem, we should remember that. That is, select one energy source only at a given time. Second, remove all the other voltage sources or current sources. How do you remove? You must always remember an actual voltage source is also having a series resistance. An actual current source also has a series resistance. Therefore, when you remove the voltage source, if it is a voltage source, you should replace the voltage source by a short. If you remove a current source, you should replace it by a open circuit. You should keep the circuit open at that place where the current source comes. And so you replace voltage sources with a short while retaining any internal source resistance of the voltage sources. Replace current sources with an open while retaining any internal resistance that you may have. Then calculate the desired voltage drops or branch currents, paying attention to the voltage polarities, how the voltage polarity is connected, and then apply your Kirchhoffs law or whatever and simplify the circuit if it is a parallel series combination and obtain the voltage. Then do that first for one voltage source. Repeat the same thing for the second voltage source, third voltage source, as many as you have. And then finally add all the current or voltages due to all these voltage sources in any given branch, and that will give you the result of the thing. I have now taken an example on the screen. You can see two voltage sources, V1 and V2, and I have again for simplicity taken 3 resistors, R1, R2 and R3. Now, so what do we do? The principle is very simple. Superposition theorem says select only one voltage source. I have selected only voltage V1 and replace the second voltage source by a short. Therefore, I have just connected a straight line here with where the voltage source V2 was there, and this is now the first circuit. I want to find out what is the voltage developed across R2. So that is what we want to do. There is no current source here, so there is no problem. So I will find out due to this V1 what is the voltage across R2. I will keep it safe, and then I will remove next time. I will remove the voltage source V1, I introduce V2, and I will put a short in place of V1 and find out what is the voltage across R2, and then I will add these two voltages to obtain the total voltage. So I will quickly take an example. I have V1 is equal to 6 volts, V2 is equal to 12 volts here, and the resistors R1, R2, R3 are 100 ohms. R1 is 100 ohms, R2 is 270, R3 is 220, and we want to find out what is the voltage across R2. We shall use superposition theorem as an example. Now what do we do? First we remove V2, connect a short. In that place V1 is 6 volts, I have 100 ohm here, 270, 220. Now if you look at the circuit, you find this is nothing but R2 actually is coming in parallel to R3 is coming in parallel to R2. Therefore the total resistance is nothing but the parallel value of R2 and R3. So I will let us find out what is R23, which is parallel value of R2, R3, and that is shown here, R2 into R3 divided by R2 plus R3. We know the formula, and that is around 120 ohms when you do the calculation. So these two R2 and R3 can be replaced by a single resistance 120 ohms. Now once I know there is only 120 ohms here, 121 ohms here as R23, I have only two resistors with one power supply, and I want the voltage across these, which is nothing but a simple potential divider arrangement. So what is Vc1 in this case? Is nothing but V1 is divided by the resistor combination R23 divided by R23 plus R1, that is the potential divider arrangement, and when I do that and find out value, it is coming to be around 3.3 volts. So 3.3 volts is the voltage when I use only one voltage source. Now I go to the other side and I keep V2 and short V1 here. Now I have again a similar situation, R1 and R2 are now coming in parallel because there is nothing else here. And what is the parallel value of R1 and R2? R12 I call that is nothing but 73 ohms by a similar calculation. So now I have a simplified circuit for V2, which is 220 ohms R3 as the series resistors, and R12 is 73 ohms. Now I find the potential divider of this and what is the voltage across R12. I calculate that here and you find it is coming out to be 3 volts. So the two voltages are, one is 3.3 volts or 3.288, close to 3.3, the other is 3. So all that I have to do is I have to add these two here by superposition theorem, that comes out to be 6.288 or approximately 6.3 volts. So you can see the values calculated. Vc is 6.3 volts by superposition theorem. If I take V1 alone, I have 121 ohms and 3.3 ohms. When I take V2 alone, it is 73 ohms and 3 volts. Therefore now let us just quickly go and do the experiment and find out whether we get these values. I have actually wired a similar circuit on the table. Right. So here you see I have 6 volts, you can see that is drawn from this power supply, and I have another voltage here that is drawn from the last power supply, which is capable of going from 12 volts to 15 volts, and the 12 volts is set there, 6 volts is set there, and I have the 3 resistors, 100 ohms R1, 270 ohms R2 and 220 ohms R3. Now let me switch on. Now you can see I have this is, what is this? I must measure the voltages. Here it is showing 12 volts, I should keep it to 6 volts. Let me measure the voltage using the multimeter. So I have connected between 0 and plus, and now let me set this to 6 volts quickly. Yeah, that is about 5.9 volts on this side. Now let me measure the voltage on this side. Using the multimeter, I will connect it to voltage range and measure DC volts. Now you can see this is 12 volts, 12.08. So this voltage source is 12 volts on this side, this voltage source from here is 6 volts. Now I want to measure what is a voltage across R2. What we will do is directly we will measure the voltage. So I will connect the voltmeter across R2, and the other end of the voltmeter I connect to the ground. So what is the voltage I get? I get 6.28. You remember we calculated 6.288. Now it is 6.24 or something like that here. So the value is reasonably close. Why is it different? It is not 6.288 because these resistors they have a tolerance band. By now you know all resistors they have a tolerance. That means what is 100 ohm need not exactly be 100 ohm, what is 270 or 220 need not exactly be 220. We calculated 6.288 with all the values exactly there, but now they can be different because these are all preferred values, and therefore you find it is around 6.23. Now we can actually try and check I now remove the 6 volts, I connect it with a short and I measure the voltage now. The voltage is 3.02 that we have already seen. When I have the 6 volts shorted and only 12 volts is there, it is 3 volts. Now what I will do, I will connect the 6 volts again and remove the 12 volts and replace it by a short. I remove the 12 volts, I replace it with a short. Now I will measure the voltage here is around 2.4 or something, right? Now it has come down, is it? Yeah, 6 volts. Now it is about 3.5. So 3.5 and 3, that gives around 6 point something. So that is the voltage we got when both the voltage sources were connected together. So superposition says that you have only one voltage source, find out what is the voltage across the R2 and remove this and connect the other voltage source. Here you connect it by a short and measure what is the voltage, then you add them together, you will get the total voltage which you will get when both the voltage sources are available. So this has been very easily shown. You can actually also measure resistances if you want. For example, after connecting, you remember the total resistance, I can now put it in resistance mode and measure the resistance. I will switch off the power supply. Now I want to measure what is the resistance after shorting on this side. I want to measure what is the resistance across this point, total resistance. This is the total resistance. This is nothing but 100 ohms plus the parallel value of 220 and 270, that is shown to be around, I have short here, yeah, this 100 ohm plus 220 and 270 etc. gives me around 219 or 220 ohms, that is a parallel. Similarly, I can measure the effective resistance from this side also, and then I can compare with the calculations that I have done already. So just I have briefly shown you how superposition theorem can be verified by having two power supplies and resistors, and we have seen that it exactly follows the idea that we already looked at. Thank you. We will go back. Right. So when you can see on the screen, the total voltage was around 6.3 volts calculated. We also got around 6.2 something, and the 121 ohms, I just now measured 120 ohms, 119 ohms or something for this, and we also measured this is 3.2 something and this is 3, and totally that gave 6.2 something. So you can see I have not measured this resistance, but in principle we can measure this resistance also in a similar fashion. Now let me move on to more important theorem, which is called Thevenin's theorem. Thevenin's theorem is again a useful theorem in network applications, and what it says is, if I have a very complicated circuit that can be simplified by replacing the complicated circuit with just two components, the entire circuit which contains several voltage sources, several resistors, I can replace it simply by two components. One is the Thevenin's voltage source and the other is Thevenin's resistance. So any complicated circuit can be simplified into two components, one voltage source and one series resistance, or Thevenin's voltage source and Thevenin's resistance as it is called. And we can there is also another similar theorem which is called Norton's theorem, which is the dual of Thevenin's theorem. Thevenin's theorem talks about voltage sources, Norton's theorem talks about current sources. Now let me just briefly explain to you, and perhaps we will try some experiments of Thevenin's and Norton's in the next lecture. Right now what we will do is, I will just give you the principle of the Thevenin circuit. Here you have on the screen any circuit with several DC sources and linear resistances connected to a load. Now what Thevenin says is, you can now replace the entire circuit here by just an equivalent circuit which contains only one voltage source, which is effective Thevenin's voltage source, and one resistance in series which is effective Thevenin's resistance. So, the whole complicated circuit can be easily simplified, and then it becomes, I can put my RL here, I should put my RL here, and the whole circuit becomes very simple. So, that is what Thevenin's theorem says. And Norton's theorem, let me quickly go to Norton's theorem and show you. Yeah, Norton's theorem is a dual of Thevenin's theorem. It again helps us to simplify very complicated network with one current source, which is called the Norton's current source, and one conductance, which is called the Norton's equivalent conductance. And then you can look at, for example, any circuit with a large number of sources and currents can be replaced by one current source IN, which is Norton's current source, and one RN or GN, which is Norton's conductance or Norton's resistance, connected to the RL, the load resistance. So, this is Norton's theorem, and the other one is the Thevenin's theorem. They help us to solve very complicated networks into very simple scheme, and then try to obtain the voltages and currents, the equivalent circuits of any arm. If you want to find out what is the voltage or what is the resistance, you can use Thevenin's theorems or Norton's theorem and solve it into, or simplify it, and then try to obtain the actual values of voltage and current. What we would perhaps do in the, what we have done in this lecture is that we have looked at the basics of what is a current source, and then we looked at basic ideas of Kirchhoffs laws, review of Kirchhoffs law, Kirchhoffs voltage law, and Kirchhoffs current law, and then we also looked at maximum power transfer law. The maximum power is transferred to the load when the internal resistance is equal to the load resistance. We also saw different conditions corresponding to the impedance and things like that, and then we looked at superposition theorem, which helps us to solve very complicated circuits and then obtain the current or voltage in any branch by trying one by one the different voltage sources and current sources, find out what is the effective voltage, and then sum them all together. That gives me the total voltage or current in the branch due to the presence of all the voltage sources. That corresponds to superposition theorem, which helps us in several circuits. Then we briefly looked at the statement of Thevenin's theorem and Norton's theorem, which help us to simplify very complicated circuits into very simple voltage source and a series resistance, or a current source and a conductance, Norton's conductance. So, we will see some applications of Thevenin's theorem, and we will also see an actual experiment where Thevenin's theorem will be obtained. That means Thevenin's equivalent circuit will be obtained for a complicated network, and then we will also see the applications of Norton's theorems and Thevenin's theorem next time. Thank you very much.